Greetings, ladies and gentlemen. My name is Orest. I'm Solutions Engineer at StarWind, and today I'll be hosting the webinar for you. The topic of our today's webinar is green IT infrastructure and why it's important for small and medium enterprises. Now, before we actually move on to the details, let's first take a look at our today's agenda. Now, first we're gonna cover up some oral information on the power consumption in a data center. We're gonna also talk about the common factors that are the most power consuming in a server itself. Also, we're gonna mention additional factors that are sometimes overlooked and do not get enough attention. And we're also gonna provide some of the infrastructure advice for making them more power efficient. And at the end, traditionally, we're going to have a short Q&A session. Well, I'm going to try to answer your questions. So let's actually move to our today's topic. Now, data centers themselves always relate with high power consumption due to their function purpose. All the equipment basically in a data center draws power. However, before we move on, just want to make one small point on data center itself. As a concept and as a term, it can be quite broad. And for one company, it can mean a dedicated building. For another, a server room, which is more of a true story when we are talking about small and medium companies. Additionally, different companies have different equipment in a data center. For example, one can have just a couple of switches and their power consumption won't add up to significant expenses, while in other cases, this can be several racks of switches and the picture will be totally different. Now, there are numerous reports already available on the web, but they all vary in proportion of equipment power consumption, and this can hardly serve as a universal measure. Now, for this exact reason, in our today's webinar, I'm not going to provide the numbers of proportion for data center components power usage, since it's quite an individual use case. What is true for one basically does not necessarily is same for the other. However, still, just to paint an overall picture that might fit the majority of companies, in the most significant power consumption factors, we include usually cooling, servers themselves, and power distribution systems, and namely losses associated with them. Again, the numbers and proportion can vary from company to company, but these factors are the most common from our point of view. Now, it is also important to understand that you most likely cannot reduce power consumption significantly by addressing only one of these factors. In fact, this requires a complex approach that takes multiple factors into the account as they are all tied together. Reducing power consumption of server components requires less power from UPS and PSU, and correspondingly results in less heat generated, correspondingly requiring less cooling and again less power consumption. As an overall, lowering the total energy cost you pay, plus also resulting in lower carbon dioxide emissions. Now, with that being said, let's actually proceed to one of the most significant factors in data center power consumption, the servers themselves. Now, it's not a secret, and we all know that capabilities of servers over decades have, of course, increased, just as their power consumption. Now, even a single server might not consume that much power, but multiply that power by the number of servers in use, and power consumption will already appear as a significant expense for many companies. Now, there are different parts of a server that consume power, but we would like to highlight the most important ones: CPUs, GPUs, and storage. Now, CPU power consumption varies greatly by the type of server processor used. On the slide, you can see that the TDP varies in a range from 105 watts and up to 270 in the third generation of Intel Xeon Scalable CPUs. Now, of course, the most important metric to look at when we are talking about chips such as CPU or GPU is thermal design power, basically TDP, which, for example, according to Intel, represents the average power in watts the processor dissipates when operating at base frequency with all cores active under the vendor-defined, well, in this case, Intel-defined high complexity workload. So in simple words, it's used as a basic indication of power consumption. More watts equals usually better performance, but also higher temperatures and more power consumption. It is, however, fair to note that TDP does not typically indicate the most power the chip could draw, but how much it draws under moreover real workload. It can, of course, draw more power, but then it's the property of the cooling system if it can deal with that. Now, of course, when we're talking CPUs and GPUs, the main factor here is your actual workload that can demand high frequency CPUs. And in that case, there is not much you can do about it. You just need those processors. But however, newer CPU generations usually are more power efficient. Sometimes this means lower or same TDP with better performance compared to previous generation of similar CPU models. Now, for example, there is Intel Xeon Silver 4108, which has 8 cores and 1.8 GHz frequency and 85 watts of TDP. Now, the next generation of Intel Xeon Silver 4208 has same number of cores, basically 8 cores, already higher frequency of 2.1 GHz, but still same 85 watts of TDP. If we take a look at the third generation of Intel Xeon Silver CPUs, namely 4309Y, it has same 8 cores, but already considerably higher base frequency of 2.8 GHz and a bit larger cache size. But of course, it consumes already more power. Basically, it has the rating of 105 watts of TDP. But however, we have to understand that in this case, we can put more workload on the CPUs comparing to other CPU generations. So basically, if we are talking about the power consumption per performance value you get, these are still power efficient. Plus, not to mention features the CPUs have, for example, with the latest generation like Intel Speed Select technology for optimizing performance. And of course, again, we get higher capacity of the CPU. Basically, you can hit more workload on it, or you could need less CPU numbers or fewer servers instead of using more servers or more CPUs of the older generations just to bear with that workload. Now, the other thing behind the CPU power consumption and its reduction is basically the technology that various vendors and CPUs themselves have. Now, a lot of CPUs, especially of modern CPUs of Intel, have a lot of features that can optimize power consumption when CPU is idle. Just as well, major server vendors introduce the capabilities to select various system profiles, and instead of setting them to maximum performance, other modes such as, for example, performance per watt in Dell can be used to save some power when workload is not significant. And in fact, in our days, that's the default profile the vendor uses. Now, this can be effectively used to decrease your CPU power consumption and to save your costs and again, but reduce the carbon dioxide emissions. Now, the next part here is GPU. Again, this is not something used commonly in all servers, and it depends on your specific workload, whether you need it or not. However, GPUs are even more power consuming than CPUs, and their range varies significantly. For example, we can see that NVIDIA A2 Tensor Core starts at around 40 to 60 watts configurable TDP and up to 350 watts of TDP in H100. And I'm talking about the PCIe cards. So in this case, I'm not even mentioning the dedicated GPU servers that you can get, basically the enclosure filled with GPUs. Correspondingly, you can already multiply the wattage you'll consume. Now, just as CPUs, GPUs also have a lot of mechanisms, basically different modes, to make them more power efficient during idle times. But another important thing that can actually help us reduce the power consumption is the virtualization. Now, traditionally, if we are talking the world of virtualization and a hypervisor, for example, you usually pass through a GPU to a dedicated virtual machine. And it's fine as long as you have only one VM, for example, that requires GPU capabilities. But in case you have multiple workloads requiring GPUs, you would correspondingly need several GPU cards all occupying PCIe slots and pass them through separately to each virtual machine. Now, this might be significantly better to virtualize the GPU, something that NVIDIA Virtual GPU or vGPU allows with VMware vSphere and just as well other brands, for example, from AMD. And correspondingly spread one or several powerful GPUs among multiple VMs instead of having multiple dedicated GPUs. Now, this of course requires licensing on various levels, but energy savings you eventually get can significantly outweigh them. Now, the final part of the most important power consumption in servers is actually storage. Now, it actually does account for significant power consumption in a server. And here, in fact, things are quite simple. Now, SSDs are getting lower in their prices and larger in their capacities. Plus, they are much less power consuming compared to HDs. Since an SSD has no moving parts, they need less power to operate and produce less heat than a regular hard disk drive. Now, HDD drives generate more heat due to the mechanical action of the disk. And as we can see, for example, the Seagate Enterprise Capacity Spindle SATA 3.5 inches 40B at 7.2 RPM consumes 6.94 watts in average operating power. On the other hand, we have Micron 5300 Max, which is a mixed-use SSD of 3.84 TB SATA 2.5H, which already consumes 3 watts of TDP. So even higher than 2 times compared to the HD consumes compared to the SSD drive. Now, this might be a wise investment both from the speed standpoint, just as well as from the power consumption as well, especially when you're looking to purchase the storage or build the new server. Now, while these are the most important factors, basically the ones that consume the most of the power on their own, there are also additional factors. Now, before we continue to the additional factors, it's also worth noting that while we are talking, for example, HD and SSD, the difference here is almost 4 watts, and it might not seem as a significant difference, right? But in reality, what happens, you probably do not have a single HDD, right, inside of the server. You have multiple of those. And moreover, this consumes more power if we are talking about the large enclosures. So correspondingly, multiply that savings by the number of drives you would have, and calculate the power savings over a year in the projected expenses. And this would already add to quite a significant sum and quite a significant savings. Now, proceeding with our less thought about factors, but still quite significant. The first point here is a server form factor. Now, usually we do not think about the server form factor as the one that could reduce the power consumption, but in fact it plays the role. So the most common form factors we usually know are 1U, 2U, and for example, blade servers and towers. Now, in fact, the 1U form factor and blade servers are the most difficult to cool because of density of the components inside of them and lack of space for proper airflow. Correspondingly, this means that most likely such servers will be heated more easily and will require fans to run faster and correspondingly consume more power. On the other hand, the 2U form factor has a better airflow, which results in lower temperatures and more efficient cooling. Plus, 2-unit form factor has larger heat sinks. Now, I believe we all know, but heat sink is a component that increases the heat flow away from a hot device, for example, CPU. So it does this by increasing the device's working surface area and the amount of low temperature fluid that moves it. Basically, heat moves into the heat sink and away from the source via natural conduction. And additionally, fans, of course, assist with this process. Now, having more space provides us with larger heat sinks, which again already provide the better natural airflow in the servers themselves, which again can save small but still relevant savings on the power consumption. Now, I also mentioned fans, so obviously fans are in our service to push air through very small restrictive airflow spaces, as well as through the small intake and exhaust areas at the rear of the server chassis. Now, the fans themselves can consume 10 to 50% or more of the total power drawn by the server. Now, to improve efficiency, many new servers and major new vendors have thermostatically controlled fans, which raise the fan speed as more airflow is needed to cool the server and correspondingly lowering their speed when the components do not heat that much, basically where you have a lower workload. And again, correspondingly, these consume less power. Now, when we are talking about the outside components of the server, the most important one here would be uninterrupted power supply, or speaking simply, UPS. Now, UPS systems maintain power to data centers in the event of a power disruption. They typically use batteries as an emergency power source that can last for some time. For example, just enough for either emergency generators to come into play or for the equipment and your workloads to be shut down properly without causing any damage. Now, when drawing power from mains, basically from the electricity grid, and providing it further to the equipment, sudden losses occur. Now, this is the result of switching in the inverter and transformers. Basically, UPS have their efficiency ratings, and this efficiency means how much of the original incoming power is needed to operate the UPS. For example, the uninterruptible power supply unit with the 95% efficiency rating will have 95% of the original input power in the load, and connected systems with the remaining 5% basically spent or wasted, if you will, running the UPS itself. However, the other important thing to note is that the UPS does not always operate as efficiently as its rating suggests. Now, when you see the efficiency rating, this means the full load, basically 100%. Now, the load factor is can basically be different. So if the UPS is operating at 100% capacity, meaning drawer full its wattage, of course it will run as efficiently as its rating implies. But if the UPS is operating at a lower capacity, as almost all do, its efficiency will be lower. Now, as an example, we can take a UPS running at 20 or 25% load. It might be able just to provide the lower efficiency, for example, of around 80%. And this is especially true for older transformer-based UPS systems, while the most recent ones, transformer-free, can allow even for 95% efficiency, even on the load of 25%. Now, these new energy-efficient transformer-free UPSs generally range from 92 to 97 or even higher percentage of efficiency. So the good and the proper way would be, first of all, to properly size your UPS to operate in the sweet spot of the efficiency with a higher load, and to make more investment initially in a UPS that will remain also highly efficient even on the lower usage. Basically, if we are talking about the operational expenses, that's where you will cut the expenses and basically also reduce the emissions. Now, another option is very popular, and a lot of UPS vendors basically market this. That's what's called the energy saving mode or eco mode. Now, this mode can boost the efficiency up to 99%. However, there is a small point that should be taken into the account when using it. Now, the UPS achieves this by actually operating as a line interactive UPS. So the load is powered by the bypass line, with the inverter inactive but ready to take over if there is main supply failure or fluctuation. Now, this can of course affect the reliability, and so this should be only used at proper times, for example, overnight or out of hours when critical loads are inactive. Now, the next very similar component is actually the power supply unit, or shortly PSU. Now, it is another important factor that is not taken into the consideration very often. So power supplies are in our server basically to perform quite a simple function, to transform AC power into DC for use by the server circuitry and its components. And this power transformation, of course, loses some energy, just as in the UPS. Now, PSUs have their efficiency rates just as well. Basically, efficiency in case of the PSU is the ratio of total output power to the input power, basically expressed in percent. And what it tells us is how well the PSU converts the AC power to DC power. Now, the efficiency of power supplied also depends on its load. The most efficient loads are within the range of around 50 to 75% utilization. Now, power supply efficiency drops below a 50% load, and interestingly, also drops at 100% load, or close to that value, unlike UPSs. Now, various initiatives exist to improve the efficiency of power supply units. For example, the most well-known is 80+, which certifies a variety of efficiency levels for power supplies and encourages also their use via financial incentives. So efficient power supplies also save money by wasting less power. They use less electricity to power the same server, and they emit less waste heat, which results in significant energy savings on air conditioning, for example. So therefore, it makes quite a good sense, first of all, to pick a proper PSU depending on the workload, because of course we want our power supply unit to cover more workload than you would actually have, but still try to hit that sweet spot between 50–75% load, or also invest in a better PSU with 80+ platinum or titanium certification that provides efficiency at around 90%, even on lower ends of the spectrum compared to bronze or silver that deliver around 80–85% efficiency on the lower and higher ends. Again, of course, it may seem that those 10% difference is not a huge thing, but it's not huge in the moment. Calculating again project expenses for a year may actually save a significant amount of power wasted by PSU directly, not to mention additional savings on heat generation and cooling as a result. Especially this is true for redundant power supply units, where load is distributed almost equally. So for example, your planned 50% of workload that your power supply unit should hit and reach that sweet spot of highest energy efficiency will be actually 25% on each power supply unit, leading to their lower efficiency. Again, that won't be a problem with the higher ratings of platinum or titanium, but this will be a problem with the older power supply units or power supply units with lower ranking, such as bronze, for example. Now, the final and probably the most often overlooked component that actually draws power is RAM. Now, with RAM, things are quite contradictory, as again, most of the companies do not take RAM power consumption into the account. And indeed, they do consume very little portion of energy. Now, the memory chips vary widely from vendor to vendor, and their power consumption is usually not well documented. But we can assume that the average power consumption for a stick of RAM would be around of the 5 to 6 watts if we are talking, for example, 3200 megahertz DDR4 RDIMM. Now, again, newer generations of RAM of same capacity consume less power than older ones. Of course, the faster the memory is, the more power it draws. However, the capacity of the single RAM stick does not scale linearly in terms of the power consumption. What I mean is that as a general rule, 2 DIMMs of the same frequency and technology will use more power than a single DIMM of twice the capacity. So for example, 32 RAM sticks of 32 GB each will consume almost or around twice as much power than 16 64 GB RAM sticks would. And this is not to mention you have some free DIMM slots in your server for future upgrades. Now, with all these factors being taken into account, there are additional overall infrastructure advice we can provide. Now, while being more and more rarely used, we still see quite a lot of cases when we use basically a service or an application per physical server. Now, this usually adds up to the piles of outdated hardware because naturally you want to make sure we squeeze the max out of our hardware investments. But you can save a lot on the power consumption and on the energy costs when you consolidate and virtualize. For example, 2 modern power efficient servers in a compact 2-node cluster can easily replace 4 or even 5 outdated physical servers with the help just of the clustering and virtualization. Now, the other thing here is the hyperconverged infrastructure. Now, while I'm not going to say that the hyperconverged infrastructure is the one fit for all solution, basically for the cases where you do not need huge amounts of storage, instead of running separate SANs or separate NASes and separate compute nodes, you can easily combine all of that storage within the compact, again, 2 or 3 node HCI cluster. And this also cuts down the power, again, on the aging hardware, plus on the additional SAN or NAS enclosures that consume power not just for the drives themselves, but also for the CPUs and RAM and the motherboards they have in themselves. And the overall logic here is quite simple. The other equipment uses much more power. It uses much more power by itself, plus it also uses more power to bear with the workload you might be putting on it. And this can be easily seen throughout all the components we will be talking about today, starting from the CPUs and GPUs and up to UPS and power supply units and up to RAM. Newer hardware can easily bear with the workload you have, can even put more on it while still reducing your costs typically spent on the power consumption. Not to mention, this significantly reduces the carbon dioxide emissions. And again, while these all factors might seem not that significant in a moment when we are talking about the 5 or 10 watts of savings, again, you can do the projected calculation for a year. And in that case, you will see a totally different number that could save on your money and plus make our world a bit greener. And now, just as I mentioned in the beginning, we will have a short Q&A session. So please, if you have any questions, let me know them in the question section. And one question we have, do NVMe drives consume more than SSDs? Yes, NVMe drives do consume more than SSDs, and to be fair, significantly more. For example, I have a node for Intel D7 P5600, which is 3.2 TB NVMe drive, mixed use. So its TDP value will be 18 watts compared of those 3 or 4 watts of the SSD. So of course, even higher than the hard disk drive, but different technology and different performance values you get. And yeah, one more question. Are you British? No, I'm not. I'm actually Ukrainian, but thanks for asking. And one more question we have, can migration to cloud reduce power consumption? That's the good question, actually. Now, does the migration to cloud reduce power consumption? I would say it depends. It depends on what exactly are we moving to cloud, basically the amount of the workload. Now, first thing to mention, we can be safe to assume that the public cloud providers already include the cost of the power consumption in the price. So you still pay for the energy expenses. But of course, it's the question, which technology would be more efficient? If you have, for example, a simple workload, a file server, a print server, or something like that, maybe a web server, and you are building dedicated infrastructure for it, well, most likely, or at least chances are that the infrastructure you build would consume more power, at least from your perspective, than you would run these as instances or services in the cloud in AWS or Azure, for example. However, if we are talking about the huge workloads, now this also means what we are talking about, just cost reduction or the carbon dioxide emission. Because if we are talking about the cost savings, again, probably you will pay less for the power consumption that is included in the price in the cloud than you would when building your own infrastructure. However, again, this might be questionable. But if we are talking about the large workloads, right, huge amounts of databases, machine learning, etc., that is all pushed to the cloud, if we are talking carbon dioxide emissions, we have to understand that we reduce our local carbon dioxide emissions, but we basically put that on the public cloud provider shoulders. So just as your infrastructure would need, their data center would also need the uninterruptible power supply units, servers, storage, networking to power all that. So when you increase CO2 emissions locally, these would increase in one's data center in the other part of the continent, for example. Now, also another question, is it true that the HDDs with the helium use less power? Now, I very well know that the helium-filled drives are more quiet. As to the power consumption, I wouldn't say strict yes or no. From the couple of researches I have read, these do consume a bit less power. What would be the actual saving in terms of the TDP or wattage? Hard to tell. The best idea probably would be to get some articles and some good researches on that. I would presume, or more likely speculate, that the power consumption would be not significantly lower. Okay, so this would be it for our today's topic. Huge thanks everyone for joining our today's webinar. We really appreciate your time and dedication to attend it. Wish everyone all the best, keep safe at all times, and see you next time. Goodbye.